Oh yeah, test 3, what we've covered for this particular test, we started back in 2.6, and we did 2.6, 2.8, 2.9, 3.1, four sections is what we covered. 2.6, yeah, that was an important one. We'll utilize the information there a lot. It was the implicit differentiation. Yeah, that's an important method because it allows us to, for one thing, if we can't solve for get y equals explicitly in terms of x, this gives us a way to differentiate those, find it's not too terribly difficult to come up with that'd be a hard one to solve for y in terms of x. But this implicit differentiation, if I want to know my dy over dx, because has a graph, and dy over dx, that's the slope of the tangent line, and so it makes sense that we should be able to come up with slopes of tangent lines to that thing. So how do you do it if you can't say y equals such and such x? Well, implicit differentiation gives us a way to do that, because if we're finding dy over dx, right, just d dx both sides, and come up with dy over dx that way. Let's see. Now, the one thing, again, I would emphasize is x squared times y. That's the easiest one to forget, that you've got to do product rule. You've got to alternate doing the derivatives of that there. So the derivative with respect to x of that would be 2x, but then it's 2x times y, because we got to do a second part to get the derivative of the y. Now, y alone, the derivative of that, if we're just looking at it, power rule or whatever, is just 1, but whenever we have the derivative with respect to x of a y, remember we've got to add that dy over dx term to that. And so all of this is the derivative with respect to x of the x squared y. And then y cubed, same deal. The power rule is 3y squared, but it's a y. We're doing the derivative with respect to x, so we need dy over dx for that. And then, of course, the right side is easy derivative. It's just a constant, so the derivative is 0. Yeah, so this gets dy over dx involved, so we can solve it then for dy over dx. Just subtract this term over, since it's not dy over dx. It's not involved there. That'll leave, gets rid of that. That'll leave these two, so I can factor off the dy over dx. Go ahead and do that in this step. It'll be x squared plus 3y squared. And that would be negative 2xy on that side. Yeah, so then we just divide off the x squared plus 3y squared. And there. So if it asks for dy over dx, that's it. If it asks for the slope of the tangent at a certain point, well, just figure out your x and y value. You have to plug those in, whatever point you're pointing it at. What if it said, what about the horizontal tangents? Horizontal tangents, what do we got? Horizontal tangents, the slope is 0, right? So if I'm wanting the horizontal tangents, start by anyway, setting that equal to 0, and then figure out solutions there. Yeah, find the equation of a tangent line. Like I said, this is the slope, just like before. So you can find your y equals mx plus b through that. Yeah, so that's an important little tool there, implicit. 2.8, that was our related rates. Three or four different types. Sometimes we start off with an equation like x squared plus y cubed equals z to the fourth or something like that, where you start with an equation and you know, say we know dx over dt and dy over dt, what's find dz over dt. I'm not going to go through the entire problem like that, but yeah, based on the related rates, what we looked at is instead of doing the derivative with respect to x, we were doing the derivative with respect to t. And so we were finding like dz over dt for this one. But it's the same idea, you're just ddt'ing both sides instead of ddx'ing. But it's this very same idea. So that was one type of equation. And I guess it's similar, like we have like the volume of a sphere. So a known formula, same idea. If you know dv over dt equals whatever, what's dr dt? I think you need to know r there too. Something like that. That type of problem. Yeah, so you've got a known formula, and you know dv over dt, and the radius here is 7. So if you know that information, what's dr dt? Now, I worded it like that, but another way to word it is, what is dv over dt? What's another way we could word that? Isn't that the rate of change of the volume? So if the volume changes at a rate of 5 centimeters cubed per second, something like that, what is the rate of change of radius when r is 7 centimeters? So this is probably more the wording we would have on that. Yeah, so this gives me dv over dt. I'm looking for dr dt, and I got the radius is 7. And so, yeah, that's the very same problem there. Yeah, these are rates of change, like we talked about in previous times. So yeah, just to kind of follow through on this. So yeah, how do we do this? Well, I'm wanting to find dr dt, so I ddt both sides, and see what that does. This would be dv over dt. The 4/3 and the pi are just constants, so we're just really doing the derivative of the r cubed, so I need 3r squared. But it's an r, we're doing the derivative with respect to t, so I would need dr dt with that. So 3's cancel, but yeah, and then, so yeah, this brings up the other point. Notice I didn't plug in, I've got r to be 7, but I didn't plug that in because the volume is changing, meaning the radius is changing as we go along. So you don't plug in a number unless it's fixed. It doesn't change as time goes along. In this case, the radius obviously had to change because the volume is changing. And that's implied in the question. But anyway, once you do the derivative, then you can plug in, dv dt is 5, the r is 7, and then dr dt. Yeah, so then we can just solve solve for dr dt. Okay. So that's another type. Just kind of thinking through the type. The other types of related rate problems, well, we had those ones where the distance between them was changing. So let's just call those the distance related rate problems. You know, we had A and B. Maybe they left at the same point, or maybe they were so far apart and one was going north and one was going south, or something like that. So we'll have one of those. Those will be on there. Oh, the trough. Yeah. Probably will have a trough. Those are the basic ones. So just to give you an idea of related rates, probably one of those. Anything, questions on that? One other thing, I was looking at the review sheet, back on the implicit, I mentioned horizontal tangent, slope of the tangent. There is probably also one where you do the second derivative, which to do the second derivative, you just work off the dy over dx. Just on this one, you do your quotient rule. Figure out the second derivative. Yeah, so that's related rates. Yeah, so that's 2.8. I mean, that's quite a bit of stuff compressed to just a small, tiny version of it. So just going through the highlights though. On 2.9 then, 2.9 was there were two basic ideas. On 2.9, it was the linearization or linear approximation. So there was a couple of formulas on it. So be sure you know those. Well, one formula for linearization, L of x, it was f of a plus f prime of a times x minus a. Yeah, and that basically what it was, it's the tangent line, but we're calling it the linearization just to point out that, yeah, we can take any function and turn it into a line. So that's linearization terminology, what we're talking about. But it only works, you have to do it at specific a values. It only works for certain values around it, close to it, for each a value there. But anyway, that's a formula. I'll probably have you find a couple of those linearization. And then the other on 2.9 was the differentials. If I can spell it. It gave a meaning, I guess, if you will, to dy and dx. dy over dx is the slope of the tangent line. So dy is actually the rise, and dx is the run of your tangent line at a particular value. But there was a couple of formulas. Dy equals f prime of x times dx. Was your formula there. You just take, at whatever x value, you take the derivative and then multiply it by the dx value, which, like I said, that's your run. You've got a curve. So at x, here's my tangent line. So dx would be your run, and then dy is your rise. That's what it geometrically means. But to calculate dy, you do the derivative, whatever the derivative value is at x times dx. And that's usually, dx is given, and the function is given, of course. And then we related it to a couple other values, and that was delta y and delta x. They're not differentials, but delta y is the change in y, and is the f of x plus delta x minus f of x values. yeah, delta change in y equals this. And then, relatively speaking, actually, how does dx and delta x relate? Those are exactly equal. So if your dx is this, then your delta x, which is your change in x, is the same amount. So those two are the same. Now delta y is the change in y value, and so that's the change in your heights of your function value, which in this case, if that's our delta x, then this, I go from this y value up to that y value. And so from here to here, that's delta y, just to kind of spread it out there. That's your change in your y value. It's just your change in your heights on the function. So anyway, you knowing that. And then, anything further on that? Is that okay? And then last but not least, 3.1, that was our last thing that we've done here. The maxes and mins, local maxes, local mins. Most of them that we did, those were the peaks or valleys. You know, if you've got corners or discontinuities, sometimes those also occur there at those, but local maxes and mins, and then the absolute maxes and mins. That's the highest point for absolute max, lowest point. These local maxes and mins are just you know, those are just local maxes and mins, peaks and valleys on a standard function like that. The absolute max and min, that would be the highest point, which on mine, I guess, whatever that is. Oh, and the other thing I'm kind of a stickler on is the actual local max here is the function value. So if that's, let's say that's a 2, that would be a local max. So f of 2, and if we had specific values there, we could give the actual height, but it is a function value, so be sure to include that. So on mine, I've got local maxes F2 and F4, local min at 3, F of 3. Put the Y value, so just call them those. But yeah, the absolute max in min, that's the highest of all points, which in this case, on mine, I meant probably should make that a little lower, but yeah, that's a little higher than this one was. So F2 would be your absolute max. Absolute min here, well, since my graph is extended both ways down, there's not an absolute lowest point here on that. So that was one part of 3.1. And then, of course, the other part was we noted that these maxes and mins were occurring at peaks and valleys. The derivative is 0, but like I said, we also had some at corners. So we talked about the critical numbers. We gave kind of a name to that. And to find those, you set the derivative equal to 0, and then the derivative, also find where the derivative does not exist on your derivative for your function. So it'll probably be a couple of, find these critical numbers. So yeah, there's probably enough there for a good little test. So we'll try to have one for you. Any questions? Ask about.